Lecture 3, Rust, Borrowing, Slices, Threads, and Traits. Okay, we've previously introduced some of the basics of Rust, including the concept of ownership. We can imagine that ownership can come with a couple of unintended consequences. We saw that when trying to pass a string as an argument to a function, that was giving away something that we actually need later. So that isn't what we want to do. What we're actually interested in that case is, giving temporarily the data in question to that function, and then it'll be ours again when it's returned. Unlike Scumbag Steve, who asks to borrow something and fails to return it, Rust supports the concept of borrowing in that you can use something and you also promise that you will give it back, and that promise is enforced by the compiler. The borrowing is always going to follow certain rules. Borrowing allows data to be shared as long as it's in a manner that the compiler considers to be acceptable. It is done in a controlled way. It is done in a safe way to prevent things like memory leaks and race conditions. The compiler will analyze all of the borrowing that takes place using a tool called the borrow checker. If the borrow checker is not certain that your code is perfectly safe, it will say no, and it will produce a compile time error. This can be a little bit frustrating because the analysis erring on the side of caution is going to sometimes say no to things where it should say yes. Broadly, the people who design Rust are of the opinion that it is preferable for the program to say no, for the compiler to say no to a program that is valid than it is for the borrow checker to say yes to a program which is not. So it always errs on the side of caution. There are going to later on be some ways that we can tell the borrow checker we're sure that the code is safe, we are willing to make the guarantee, but you have to be sure, otherwise all the usual bad things can happen, race conditions and memory leaks and other things that you generally speaking do not want. So with that in mind, let's talk about the borrowing implementation. Now, how to borrow? The feature that we need for the concept of borrowing is a reference. And the reference uses the ampersand symbol in C. This was the address of operator. Here it's the ampersand, and that's probably what we'll call it. The reference operator, its official name, appears both on the function definition and the invocation. So when you are defining the function, you say, I want to take as a parameter a reference, and then when you are calling that function, you also use the ampersand symbol to say, I am providing a reference. This makes sure there's no possibility of confusion as to whether a reference is expected or a reference is provided, or if instead ownership is supposed to be transferred. So in the very simple program as below, main creates a string s1 and calls then function calculate length with a reference to that s1. This is a borrow, so calculate length borrows the string, uses it to compute the length by calling the length function on it. Nothing super exciting there. And then when we have returned from this function calculate length, that borrow is finished. It is returned, main has it back. So the reference that is created when we call address of ampersand s1, reference to s1, goes into the function calculate length. The borrow takes place at the time of the call, and the borrow ends when that function is over, when the reference goes out of scope. So a reference is important to distinguish from actual ownership. It's part of the ownership system, but it isn't the same as ownership in any sense. A reference cannot exist without the original owner continuing to exist. As we see here, S being a reference is pointing to S1, S1 being the string that we defined previously, using this diagram here from the official docs to illustrate it. And so you can only borrow something which does in fact exist. and that obviously prevents us from borrowing something which has gone out of scope or otherwise has some sort of issue. Borrowing also implies that the thing being borrowed has to live long enough for any valid reference to it to continue to exist. Otherwise, you're borrowing something that was destroyed, and we can't have that. Now, when you borrow something, you can't do with it whatever you wish. It is not yours. You are just being granted, a form of access to it for a period with some limitations. For example, you can't assign ownership of something because you don't own it. You can't give someone ownership of something that you yourself do not own. If you borrow your friend's car, you can't then give away the car to somebody else because it's not yours and you don't have the authority. And by default, when you have a reference, the reference is immutable. That is, you cannot change the thing, even if the underlying data is mutable. So if the string S1 is declared as mutable, but you have an immutable reference, you cannot change that string. Mutable references exist, but like mutable variables, they must be explicitly declared, and you specify saying you want a mutable reference, and again, just like we are specifying on the creation of a reference, you specify ampersand mute, both at the call to the function and in its definition. So again, we have to be very explicit about when we want things to be mutable. By default, we don't want that. Quite honestly, I think in real life, you would be much more agreeable to letting people borrow your things if there were strong guarantees that number one will always be returned and number two is always returned in the same condition. That would be nice. Until such time as a magical technology is invented that supports those guarantees for real-life objects, no, you may not borrow my car. Sorry. Now, there are some rules related to a mutable reference, and that is actually important, and these rules exist to prevent certain possible race conditions. So the first one says, while a mutable reference exists, the owner cannot change the data, and the second rule says, when a mutable reference exists, it can be the only one in existence at a time, and when there is a mutable reference, there can be no immutable references. As you will imagine, thinking to our previous discussions about how race conditions work, we have perhaps two concurrent accesses to the same memory location, one of which is right. You can see how the mutable reference rules prevent this problem. Because, well, if a mutable reference exists, there could be competing rights if you're allowed as the owner to change the underlying data, so that should be forbidden. And if there are immutable references at the time where there is a mutable reference, someone could change using the mutable reference, and that results in a race condition with the reads of the immutable ones. So the goal is to prevent any possibility of a race condition. Now, the other thing that happens potentially when we use immutable references specifically is there is a slight performance increase that could be possible where you can cache values, including in CPU registers, but we'll come to that later, without worry that those values will somehow get out of date. And as long as we follow these rules, then there won't be race conditions. And of course, the compiler's borrow checker will see to it that you follow these rules, even if it seems kind of painful. And as long as there are no mutable references, you can have arbitrarily many immutable references all at the same time, because as you will know, reads don't interfere with reads, so there's no issue there. There's no possible race condition. And as I mentioned earlier, references cannot outlive their underlying objects. So when we do something like this, if we say let reference to nothing equal dangle, and we call this function dangle, and it returns a reference to a string, the string s is declared here as the first line of that function, so we create it using string from and the text hello. We try to return a reference to this string. Now, in C, this would be a dangling pointer, because you could totally do this. Obviously, in C, there would have to be an explicit deallocation, but if there was the explicit deallocation at the end of function dangle, but you returned a pointer to S anyway, it would not be a compile time error. You can see this a lot in C programs where somebody has stack allocated a structure and then wants to pass it to another thread and does so using address of. It compiles and might even work at runtime sometimes, but it is wrong and will eventually be exposed as a bug and come back and bite you. If you actually try to compile this code example, the compiler says something about giving the value a lifetime. We're going to talk about lifetimes in an upcoming lecture. It is a little more complicated than is appropriate for right now, where we are in terms of understanding ownership, but we will get there, rest assured. There is a more recent improvement in Rust's borrow checking. In the most recent version of the rules, a particular check was made less strict, called non-lexical lifetimes. And before this change was introduced, the code that's shown here wouldn't work, because it would say, well, look, I see that on the last line you want to create a mutable reference here to X. We're going to assign it to Z. But that's not allowed because the previous reference, Y, was still in scope. Now, that's true. Y has not technically gone out of scope until we get to the end of main. However, with non-lexical lifetimes, the compiler can identify that Y is no longer used after the printline macro is invoked, and therefore the Z reference is okay to create. Y can be dropped as soon as it's no longer needed, and the Z reference will not exist at the same time, so all is fine. You could picture that under the old rules at the end of function main, that Rust's compiler would insert the drop statements that cleaned up Y and Z and X and everything there. However, under non-lexical lifetimes, it can see that as soon as the print line for Y has happened, Y is no longer needed, and we can drop it. We can get rid of it there immediately, even before the let Z equals statement is executed. So in that sense, all is fine, and non-lexical lifetimes do add a little bit of improvement to the borrow checking rules, just for quality of life of the programmer. All right, what about a slice? The slice concept exists in a few other programming languages. If you've written something in Go, you might be familiar with the idea of a slice, and if so, that will certainly help. But if not, they're not super difficult. A slice is a reference, yes, a reference as in, the kind of reference we just talked about in ownership rules, to a contiguous subset of the elements of a collection. This is what you do if you need a part of an array, a typical example of that being a substring of an existing string. So you have something that looks like this. We declare a string, let s equal string from hello world, and then we create two slices, hello and world, and they are the subsets of the string 0 to 5 and 6 to 11, respectively. And we'll see, actually, that this dot dot notation is used in the array index for a string if you want to select a range instead of in other languages where it might be a substring where you put the start index and then a comma and then the next index. Here it's two dots. We'll see the same thing in for loops as well. It's just a way of representing a range, and we're saying, yes, we have a range. It is from 0 to 5. And so this gives us our substring, if you will, as a slice. Now, the reference is, as with other references, referring to the underlying string s, so that reference can only be valid if the if the underlying string is itself valid and it can't go out of scope. As with other kinds of reference, the existence of a slice prevents modification of the underlying data. You can you can avoid race conditions again by sticking to that behavior. And slices can apply to vectors, which we've already briefly seen, as well as any other kind of collection. It's not restricted to strings, but a string is a nice, convenient example for this purpose. And slices, again, are intended, like references and borrowing, to prevent race conditions on collections, so they still follow the rules about mutability and not being able to change the underlying data while there are references to it. This not only helps avoid race conditions, but also potentially prevents copying data, keeping in mind that copying is usually kind of slow. Now, one of the things that we've skipped over briefly is that a lot of functions that we use return a result type. And if you're just getting started and you're calling some function and you're thinking, well, I asked for a value, but I don't get the value back, it says I have to do something, it's probably because that function returns a result. And result has two options: OK, and it contains the actual type that you asked for, or error, and error contains some sort of error message. One of the things that we try to encourage, but don't necessarily do a good job of encouraging in earlier programming courses, is the idea of checking return values from functions. In particular, you want to bind a socket so you can do network communication. Well, you should check the result of bind to see, was it 0? If the result was 0, then you did successfully bind the socket, and if not, something is wrong, and you can look in the error numbers and you can find out what's actually kind of going on. Rust tries to encourage making that a bit more explicit, in that a lot of functions return a result, and result here with capital R. And if everything went fine, then result returns the value you are expecting. If something went wrong, it gives you some information about what actually went wrong. You have to unpack that result to get the type that you want, but the goal is to make it explicit that this could fail, and you should be able to handle that. So, for an example, if you try to open a file but the file doesn't exist, that's an error, but the error is foreseeable, in that it is possible to imagine in advance that when I want to open a file, that file does not exist, right? This is not such an unusual, exceptional situation that we just don't know what to do with it. If it doesn't exist, well, okay, that happens. Users delete files, or they rename files, or whatever else has happened. And so, ultimately, because the system call that we're using to open the file returns a result, we have three ways of handling it. And there's a match expression, unwrap, and expect. There's some shorthand notation for some of these, but match, unwrap, expect. Well, the match expression is like a switch statement. It is, you specify what you are matching, and there are branches, and whichever branch you match is the thing that you execute. Okay, that's fine. Unwrap is the quick way to get the result. It gets you the results if it was okay, so it unpacks it for you and returns it to you, or it calls the panic macro if there's an error. And panic is like throwing an exception. It is saying, I don't know how to handle this, and the computer is panicking and freaking out. And, well, that's not great, but panics will happen sometimes, and you will probably encounter some when you write code. If you write something where there's an error or something that we just don't handle, then panic is how the application deals with this situation it cannot deal with. That's fine. There's also expect, and expect is like unwrap, except it allows you to add some more information to what you tried to do. So if you use expect, you can specify things like, unable to open file, and writing that error message for yourself is going to be a little bit nicer and perhaps make it a lot easier to track down where in the code something went wrong, so you can see, aha, this is the exact message, then that really helps. So you might be tempted to always use unwrap, which, like Wile E. Coyote discovers here, has a slight tendency to blow up in your face if something did actually go wrong, because you don't handle the error very gracefully. And I suggest that you use expect more because you shouldn't deny yourself the opportunity to add the debug information that would help you to figure out exactly what went wrong. And the other side of that is you should use result types for functions you write if things can go wrong. Make your future self happy by providing the information that you need to debug what has actually happened. Errors will occur. And accounting for that upfront is better. And not accounting for unhappy outcomes is common, not just in programming, but in business. I had a long debate with somebody about goal setting in the team, and it came down to they wanted to set as a goal for the team that 90% of companies get approved within 2 days. What they're getting approved for isn't relevant in the story. And what I said was that actually what we should do is write that as 90% of companies get a decision within 2 days, because no is a valid answer. And the same thing applies in your code. Errors are possible outcomes. They're not so impossible to imagine that we never have to think about them, we never have to deal with them. So using a result type is an explicit acknowledgement that things can go wrong and we can recover from it, as long as we address it appropriately. So make your future self happy, use result types. There is a small performance penalty for that. There's no free lunch in the world, and there's a some data from CS 343, which had a performance comparison of exceptions versus error codes. And exceptions that don't happen are faster than explicitly handling error codes and result types, because there is some extra work to create the result and then to unpack it on the other side. Makes sense. But both checked exceptions, the kind where the compiler would say you need to handle this exception, and result types force the programmer to explicitly deal with the error, even if that's explicitly ignoring them as opposed to silently ignoring them. And so yeah, it is better in that sense, because your time in terms of debugging what went wrong is valuable, and that's something that you could save by having a little bit more time invested into developing the code and putting the result types, even if it comes with a little performance penalty as a result of creating and unpacking those result types.